Let me start now again. So we saw monitors, we saw the programming pattern for monitors. Let me now show you how to implement monitors. So it's as an extension of locks. Remember how the reentrant lock works? So let me go to the slides. So let me show you now how to implement monitors. So remember we saw the programming pattern, how to use monitors. Now let's see how to implement them. So a monitor starts as a reentrant lock. So remember how reentrant locks work. They use exchange for managing the tokens. They use the thread identity, current thread, for checking to see if we're already in or not, and there's also exception handling with try finally. So we're actually extending this. If you think that was complicated, this is a little bit more complicated. So we're going to make two changes here compared to reentrant locks. First of all, we're going to slightly modify the interface of the lock. It's called a get release lock, so that entering and exiting are two separate operations, which we call get is to go in and release is to go out. Because of this, because we need to get in different places. So we get in when we have the lock, but the wait operation also has to try to get in, and it also has to release the lock. Okay, so there is we're using it in several places. So we are going to have a get release lock, and the second point is the wait set. We're going to add a queue. You see that queues are really used a lot. So the reason why we implement it as a queue, and the wait set is implemented as a queue, because it ensures fairness. So queues are very nice for fairness. You put a thread in the queue, and the thread moves along the line, eventually comes out. So the oldest threads come out first. So it's not possible for a thread to stay in the queue forever. If you're using it, the threads will always be moving through and the old ones will be coming out. This is also why when you go to a store, people wait in line in a queue, because they don't wait forever, okay? It ensures fairness so that everybody waits about the same time. That's why it's not implemented as a stack. If you implement as a stack, you put on the top, you remove from the top. The threads in the bottom of the stack, they might stay there for a very, very long time. So stack is not fair. So that's why we implement it as a queue. So the wait set is a queue. And we extend slightly the queue that we saw before. We have a delete all. So we have one operation that lets you take all the elements. We have size, which lets you find out what is the size of the queue. And we have delete non-block, which immediately returns the element, or it's like a delete, but it also tells you if the queue is empty. It either returns a list of one element or nil if it's empty. So immediately tells you if it's empty. So with this, we can implement the monitor. So the first thing is a get release lock. So this is actually a modification of the reentrant lock. So instead of having a procedure with the exchange and the leaving the around the procedure execution, we actually now have two operations. We have get lock and we have release lock, but you can see they're actually doing the same things. So get lock is what happens just before the critical section, and release lock is what happens after. So here the get lock is going to do the token managing here with the exchange. It's also going to check the ID, and it's going to return true if it actually had to go in, if it had to do something with the token. It will return false if it's already in and did not have to do anything else. And the release lock here, notice it's not doing the exception. We will do the exception in the other piece. It's just passing the token, that's all. And we need another cell to make sure that the get and release can talk to each other. So the new variable in the get is put in a cell, token 2, so that the release lock can actually release it. So we need this extra cell, and it has to be a cell because we can call get lock and release lock many times, of course. So it's not always the same. It has to be updated. So the lock then has two operations, get and release. Okay, so that's a get release lock. We also extend our queue. So here we have a queue. Remember, I'm going to use the one with cells and locks. So here we have the cell with the queue state. The insert and delete are as before. We also have a standard reentrant lock to implement the queue. You see, we have a get release lock, but we have also a lock that we need to implement the queue. There may be more efficient ways of making it only one lock, but here I'm doing a separate lock so that we actually have a separate queue. We have the size operation, which basically just tells me the size, returns the size. We have delete all, which returns a list of all the elements. Basically, it takes the S, which is the reference to the front of the queue, it binds the tail to nil, and that turns S into a list, and then it makes the queue empty. It does an assignment so that everything is removed. And then there's the non-block delete, which checks to see if the size is bigger than 0. If so, it returns a list of one element, which is the delete element, or else it returns nil if it's empty. So the delete non-block will actually tell me if the queue is empty. So this is my queue with my extra operations that I need for the monitor. Okay, so get release and extended queue. And here's actually the code for the monitor itself. So I have a queue and a get release lock. First is the actual lock. So this is the lock as before. So the way it works, if L.get, then try P, finally L.release, else P. So this, if you look carefully, this is exactly the same code as before for the reentrant lock. Okay, so this is a standard reentrant lock as we did before. It's already kind of a complicated implementation, but it's there. Now we have the wait operation. So this one is managing the insertion. So how do we insert a thread in a queue? What is a thread? Well, basically the thing is we want to suspend the thread. Okay, so what we're going to do is we will create a new unbound variable, a data flow variable. We will put this variable in the queue, and this variable is how we manage the suspension. We will then do a wait on X so that the thread suspends. But you can see the X is actually in the queue. So if some other thread binds X, then the thread will continue. So this gives us the effect of suspending the thread and putting it in the queue. Notice here we release the lock. So we insert into the queue and then we release the lock. This is why we need a get release lock, because we're doing the release in two places. Then we do the wait, and after the wait we do a get again. So you see there's like a combination of release and get. In the lock we will do get and then release, but inside when we do a wait, remember we already did a get in the main lock, we will do release, and then eventually when the thread continues we do a get again. Okay, so there's always get release, get release, get. They're always paired. The original one is get followed by release, but if we do a wait, then it will put a release and then another get. So if we get the effect of get release and then another get, and finally at the end a release. So if you do more than once the wait, you will always get release, get release, get release. So this is how we implement the wait. Now we have notify and notify all. So the difference between notify and notify all is that it's only one or it's all threads. So notify removes an arbitrary thread. So basically we do delete non-block. So if it returns a list, that means we have one suspended thread. We make the thread continue by doing x equal unit. So the waiting thread will continue. Otherwise, if the queue was empty, we do nothing. Skip. the notify all will delete all. And so L is actually a list of variables. So it's actually a list of suspended threads. So for all x in L, we do x equal unit. We start them all up again. We start them all up. And of course, they're all going to try to do L.get then. Huh? So you can see how it works. You can see specifically here that the get operation, that after you do a wait, when the wait continues, that it immediately does a get. Okay? So that when you go out from the wait, you will immediately do again a get operation. Okay? So that's part of the wait. Okay, for the implementation. This is actually quite a subtle implementation. The original edition of the book actually had a bug in this implementation, but as far as I know, this is actually a correct implementation. Okay? Okay, so let me conclude now for monitors. So you see that we actually extend locks, and we can suspend and resume threads depending on conditions. So notice that there is only one wait set for the monitor. There exists variation of monitors when you have as many wait sets as you need. You define a separate wait set for each condition. So non-empty is a wait set, non-full another wait set, and so on. So the programmer declares that. Some languages do that. That gives you more efficiency if you have contention. So because in the Java implementation, the same wait set is used for all of the conditions. So if you have a lot of contention, it can be slightly inefficient, but it makes it much simpler. And in practice, usually you don't have so much contention. If you have so much contention, then there is something wrong, and you have to restructure your application in any case. So that's the Java philosophy. So the wait set is managed by wait and notify to add and remove one thread. And in practice, though, we're almost always going to use the notify all operation. There's actually a book on concurrent programming in Java. Concurrent programming in Java. You can get second edition by Doug Leah. This is all about programming with monitors and things, and so it gives you lots of special techniques. So it can get complicated, but basically a lot of it is actually building abstractions using monitors and using them, building thread pools, building tuple spaces, and so on. So basically trying to get rid of monitors by using them to build abstraction to do something else. So monitors are actually difficult to program with unless you use a pattern. So this is what I recommend for you, to always use this general pattern, because otherwise you will have problems. Okay? So that's about monitors. So now after monitors we will talk about transactions. So let me go back to the chat. Okay, so is that clear? So there's a question on the monitor implementation. Why does L-get in a condition statement that just skip? Okay, let me go to the slide and I will show you the implementation. That's a good question to understand how the implementation works. So why is the L-get here? So the L-get, so remember how L-get works. So the L-get is this, it's the get lock. It returns true or false. So it returns true if it's the first time that it's going in. It returns false if it's already in the lock. So if it's already in, then it doesn't have to do any work, and it would be buggy to do it. You don't do anything. But the first time, it has to be true. So we have to understand that here. So here, if LGet returns true, then we have to do the try finally, and we get in and the release. But if the LGet returns false, we're already in, so it's enough to do P. Okay, so in the wait, we will also do a get to get in, but maybe we're already in. So if we're already in, we don't have to do anything. But if we want to get in here, so if it returns true, then we're getting in the first time. Okay, but the wait does not execute any code. The code comes after. Okay, so the wait is, so here we get, if it returns true, we don't actually have to do anything because we have just gotten into the lock, but there's no code here in the wait. We're already in, the code will be, the thread is already executing the code. We just have to make sure we get the token. Okay, so that's why it returns, it does skip. It basically doesn't have to do anything when it's true, and it doesn't have to do anything when it's false. Okay, so is that clear how it works? So it's the way, it's because of the wait, because the fact that you wait has to get in. It's because the wait also gets in, but it doesn't have to do anything else than just get the token, because the actual code is already, it's the main lock has already done that. The main lock is already set up to do a try finally. Okay, all of that is already set up. The wait, the LGet in the wait just has to get the token to make sure that it's actually in the lock. Okay, is that clear? It's a kind of subtle implementation, huh? So, but it's good to see it, to see how these kinds of abstractions are built in a concurrent system. So in the, just for a remark, in the exam, I will ask you, I can ask you to tell me how reentrant locks are implemented, but the monitor, I will not ask you to show me the code, but I might ask you to, I might give you the code and then I will ask you to explain it, okay? So I will not ask you to reconstruct the monitor implementation, but I may ask you to reconstruct the reentrant lock. So the reentrant lock is actually conceptually fairly simple, so I want you to be able to show me the code for a reentrant lock. So it's not needed really to memorize it. You just have to understand how token passing works. You have to understand how the thread identity works, and that you need also to handle exceptions. And then you can rebuild the entrant lock. But I'm not going to ask you to rebuild the code for monitors. Okay? So now let me go to transactions. Is that clear? So monitor is a complicated thing, yeah? You can see it. Now we're getting into complicated things. In my view, monitors are not a very good way to bake concurrent programs because they're complicated to use. They're also somewhat inefficient because of the contention issues, but they're still widely used. So many languages like Java use them all the time. But so if you have to manage these applications, you have to understand it, how it works. But if you want to write a new application, I do not recommend that you use monitors. Okay, so let me now go to transactions. So the final concept that we're going to see on concurrent systems in this course, which is transactions. So let me go to the slides here. So transaction, again, is an extension to a lock. But a transaction is a concept that's used for databases. So now we're not worried about managing multiple thread and abstraction. Now we're managing data. Okay? We have a large database, a huge amount of information that we have to update. So we will update the database, but the database is important. So we want it to survive even if there's a crash. So we will have concurrent updates and we will have crashes. So the database has to survive crashes. So this is the critical problem we're solving, that transactions solve for us. So large databases are incredibly important. Okay, so many large companies are based on that. 100 years ago, it was all written in books and people were writing down the books. But to nowadays, all of the critical information of large companies is stored in these large databases. And if the databases disappear, the company will basically go bankrupt. It will not be able to continue. So it's critical. So it's the core of large companies. Your bank account is stored in a database. The amount of money you have, it's stored in a database. Okay? All the personnel, all the parts, procurement, everything, it's all stored in databases. So a database is a critical part of the computing infrastructure, and it is implemented to be completely resilient to crashes. So it's probably the most reliable software that exists, is the software for database. It has to be resilient. So resilience is a technical term. Resilience means that it survives crashes. We can even say how many crashes. So the information must survive even if the computer crashes or the disk that stores the information crashes. The information must survive. So there's a whole course and books are written on how to make systems resilient. The basic idea is to use redundancy. So the database is stored in multiple copies. So if one copy crashes, the other copy survives. And then when you update the database, you have to update both copies. But the problem is also that you can crash during an update. So you can see it's very tricky, and we'll explain how this is done. So the crash can happen anytime during the update or after, and the database must survive. So this is why it's implemented. The second is performance. So we really are very demanding on this thing. Databases, it's not enough that they survive, they have to be fast, because the bank will have customers, and if the customer has to wait days for doing a transaction, the customer will not be happy and will go to another bank. So the transactions have to be done quickly, a large rate of concurrent updates, and finally, scalable, large numbers of clients. Banks and companies, big companies, they have thousands or millions of clients. Okay? So a large bank typically has millions of customers, and all of the information for all those customers is stored in the database. So you can see the database is one of the most impressive pieces of software that exists today. Okay? And transactions is how the database is accessed. So the question is, how do we achieve all these three properties? And it's not simple, but they are achieved. So this is one of the most impressive results of computer technology, that we can actually achieve it. So let me show you some example to motivate how it works. So here's my database. It has information. So we represent it as an array of cells because we can update them. Here we have 1,000, but in real databases we can have much more than that. We can have billions of these guys. So it's huge. And we want to update this database. So let me start first on the update, and then we'll talk about resilience. Many clients want to update. So how do we do it? We have this huge database, and many clients are doing concurrent access. Well, it's very simple, right? We use a lock to protect the database. So we can have a lock. Let's say we have a single lock. It protects this whole array. But that's a problem. We have millions of clients. Maybe 1,000 clients want to do transaction at the same time. Okay? Whenever you go to an ATM machine to take money out of the wall, you're doing a transaction. It's doing a transaction. Whenever you buy something with a credit card, it's doing a transaction on this database. But this single lock is a bottleneck. If the client locks it, no other client can do anything. So if there's a client doing this apart, here there's a client A, then client A, client B is blocked. Okay? So client A is doing stuff here. It's very happy. But client B is blocked. But why is that? That's not logical, because client B is using completely different part of the database. There's no reason really why client A should be blocking client B. It's kind of artificial. So this is a very naive implementation. So the real system, we want to do much better than this, okay? This would be very, very slow. Okay, so let's improve it. Let's improve it. Let's put in one lock per cell. Okay, so the L's are locks, the C's are cell. This is much smarter because we can have a client here, client A, and we can have client B here, and they don't interfere. If they use different parts of the database, they can actually run at the same time so that the system will be very fast. But what if there's a conflict? Let's say we have a bank account here. Okay, each of these stores money, an amount. Okay, let's say we have a transaction T1 that transfers money from C1 to C2. These are two accounts. Transfer money. Let's say we have another transaction T2 that transfer money from C3 to C2. So C2 is very happy because he's getting money from C1 and getting money from C3. Okay? So how do we do this with the locks? We have to be very careful. So what if these two transactions are overlapping? What if T1 reads C1, T2 reads C3 and writes C2. Okay, it's complete. And then T1 writes C2. Well, the C2 is going to forget the number coming in from C3. So the value in C2 will be incorrect because there's interference between them. So the updates have to be atomic and they have to not interfere. Okay, so atomic means we will remove money and add money. So the total amount of money is the same, but not interfere. If the two of them are concurrent, they shouldn't step on each other's toes. So this is what we want to do to get the high concurrent updates. We want to guarantee this. But how do we do that? So that's the question we are going to solve here. Okay? Okay. So let me now summarize what transactions are doing and why we need this transaction concept. So first of all, each transaction, I call update, can do many operations. You're transferring money, but it's not only transferring money, you're also updating the auditing, you're keeping track of other information. So bank keeps track of a lot of information. So again, we have a large atomic action, kind of like the reason why we need locking. Also, we don't want to have interference. If I have two concurrent updates that are modifying the same part of the database, they should not interfere. So that's the first thing. Second thing, the system can crash. Okay, Again, now we're talking about resilience. It can crash at any time. And in order for things to be permanent, the database is stored on a disk. But many things can go wrong. The computer can crash. The disk itself can crash, can break. Okay? And so everything has to stay correct. So if I'm doing an update and the system crashes during the update, maybe it's not possible to finish the update. So what can we do? There's actually only two things we can do. Either we commit, that means we do the update, or we abort. That means we do not do the update and it's as if we do nothing. So if the update is done only partially, there's no way we can make it complete. We actually throw it away completely and we keep the initial state. So when you do a transaction, you can always have an abort. That means that you keep the initial state. The transaction, when it aborts, that all the work you did, maybe it did some of the work, it all is thrown away and you guarantee to have the initial state. So how is this implemented? Well, let me give you an idea. So the update can do many things. What happens if the computer crashes? Okay, if the disk crashes, we will have another copy of the disk. Let me just say, what happens if the computer crashes? And then you reboot, and the disk has corrupted information on it. So how does that work? Well, the way to do it is that while you're doing the update, you store it in a special place on the disk. All of the new things. When the update is complete, you will switch the old data to the new data on the disk. And in order to do that, you write one word to disk. Basically like a switch. Ching, from the old to the new. So this assumes that the disk, that you can write words atomically. And this is actually correct. You can actually write blocks atomically on the disk. So ching is correct. If the disk crashes before this one word write, then the new information is thrown away. It's an abort. If the disk crashes after the one word write, then it doesn't matter because the data is already existing on the disk. When we reboot the disk, we will see the new data, and it's a commit. Okay? So it's this one word switch that makes sure that the disk is actually correctly doing commit or abort. So that's this. So I'm not going to say more about this technology, though this is something you can read about otherwise. What I will talk about is that you can have many actions in parallel. You can have multiple updates accessing different parts of the disk at the same time. But for performance, as long as they don't interfere, they can execute in parallel. And you have to make guarantee that they will not interfere. Okay? So that's the real trick for transactions. How do you guarantee that they don't interfere? Okay? So transactions, you see that they have a bunch of requirements. They are actually, there's a huge implementation behind this transaction thing. And people talk about ACID properties. Sorry, ACID properties, because it's an acronym, okay? For some reason, there's 4 important properties for transactions, and they start with A, C, I, and D. So people say transactions have ACID properties. So these are the most important properties of transactions. So there's atomic, consistency, isolation, and durability. So atomic means that the disk will do everything or nothing. It's what I just explained. It's like a single operation. So that's atomicity. The operation is atomic. Consistency means that we respect the invariant of the database. When I do an update in a bank, for example, I'm transferring money from one place to another, then the total amount of money in the bank should not change. If I remove 100 euro from one account, I add 100 euro to the other. I will not add 95, okay, and stick 5 in my pocket. No, that's not allowed. I have to respect the invariance. So that is called consistency. That's the second property. Notice this property is actually the responsibility of the programmer, whereas atomicity is a responsibility of the implementation, of how the transaction is implemented. And then we have two more properties. Isolation. This is what happens when you have concurrent transactions that are doing on the same data, transferring money between the same accounts. They shouldn't interfere. So isolation means transactions don't interfere. We know that they're atomic, but that's not good enough. If the two transactions are concurrent, they shouldn't actually be able to step on each other's toes. Okay? So this is called isolation, and it's also called serializability, but people like isolation because it fits better in the acronym. But people talk about serializability. So the idea is if you do two transactions that access the same data, it's as if they were going in some order. So it's as if it's sequential. So the implementation is actually parallel, but semantically, one of the transactions will always be before the other ones. The other one. And so it's as if the database will change as if they're done sequentially, even though they're actually executing in parallel. So that's called isolation or serializability. So this is very important, of course, for performance. And the final one, durability. Durability is also called persistence. It means that it survives crashes. That means that there's a stable storage, like a disk. Stable storage. That even if the computer powers down, even if there's no power, the system will survive. So this is important for all real-world implementation of transaction. Durability. Very commonly, this is also called persistence. The data persists even if the power is down. Okay, let me go to the chat. So I said a lot of things there. You can see transaction is important, huh? Okay, so let me look at the question. There's actually another question on I'm not sure if it's about transactions or monitors. Keeping track of changes. Okay, so I think this is a question about I think this can be a question about monitors. So I do a put, I do something, and then I do a get, and I do a put, and I do a get. Well, you can do some kind of optimization. The question is, we combine somehow the writes, and then into a single thing, and then we combine somehow the reads. It is possible to do things like that, to do kinds of optimizations, to be smart, and to combine multiple operations in one. That is possible. And sometimes it's good to do that. But I do not talk about now because I want first to explain the main concept. So I'm not sure what the question means, the question from Lorenzo. But let me go to a question from Simon. How can transactions work to be as if sequential but parallel in truth? Well, that means that if the two transactions are not interfering at all, then they will be actually in parallel. That's clear. If they are partly interfering, maybe there's one cell in common, then you arrange it for one of them to do that cell before the other. So it's like partly sequential, you see? But still as much parallel as you can. So the idea is that if you have two transactions really interfering with each other a lot, they're using exactly the same cells and they're doing stuff, then of course you cannot run them in parallel. You have to really run them sequentially. But in the program, I have two threads doing transactions. So it looks parallel, okay? Look, they're concurrent. It looks like they're running parallel. But in really, they'll be doing sequential. So in order for that to be very clear, the programmer imagines that even if I'm doing lots of transactions concurrently, the system will be very smart and will make them sequential if necessary, and the ones that are independent will be parallel, so it will be as if they're sequential. So I can assume they're all running sequential, but the system will make the ones that are not interfering, will make them in parallel, okay? I'm not sure if that's completely clear. So it's a question between semantic and implementation, huh? So the programmer thinks everything is sequential, looks like it's sequential, and the system tries to make it parallel. If that's allowed for the sequential semantics, if the two are independent. So the system tries to run it in parallel, but still making it seem that it's doing sequential. It only works if they're independent, huh? If they're really interfering, it has to really do sequential, huh? You see? So the idea, but the programmer can reason about transactions, can do is thinking as if they were running sequentially. So that's how things can be simple for the programmer. Okay, is that kind of clear? So let me go back to the slides here. Okay. So there's also a concept of lightweight transactions. So remember, in a bank, the transaction is stored on a disk and it's persistent. So it survives even if you have a crash. But sometimes that's not needed. Sometimes you don't need persistence. You want the nice ability to do commit or abort, but you don't care about persistence. They're like programming abstractions, these transactions, okay? It's simply an abortable atomic action. So if there's some problem, then the program code is fixed. Actually, this is kind of a smart version of exceptions. Remember, we do exceptions when there's a problem, like you try to read the file, but the file disappears, poof. Well, then you have an exception and the program has to fix all the wrong variables. Well, a transaction will do that automatically. All the variables are restored to your initial values, and this is all automatic. The transaction does this. So a language that provides a software transaction or lightweight transaction, what's called a software transactional memory, that's usually what it's called. So the lightweight transactions, they're not durable, they're not persistent. But if there's a problem, all the variables are automatically restored. So this is, of course, more work. It's not so efficient, but it's much easier for the programmer. So there are languages today. This is also called STM sometimes, software transactional memory. Software transactional memory. So when you see people talking about STM, this is what they're talking about. It means that you have everything except not persistence. That you don't care about disks and stuff, but you want to do your program might have problems and you want to handle it. So this is a variation of transactions when you don't need persistence. Okay? So let me now talk a little bit about how we implement transactions. So it's a big area. Implementing transactions is a huge industry. You can imagine that because there's so much money involved, because it's so important for companies and banks and industry, that there's a huge amount of work. And so all the techniques that people use to build transactional system, it has a name. It's called concurrency control. It's kind of a strange name, but whenever you build a transactional system, you need to do what's called concurrency control. Okay? So we're going to explain part of concurrency control. We're going to give you introduction to concurrency control. We're going to actually show you how to implement these light transactions. We're going to give you an actual code for implementing this, and the algorithm we're going to do is a very specific form of concurrency control called optimistic concurrency control with strict two-phase locking and deadlock avoidance. So the red parts are special ones that we choose, and we will explain all of that so you will understand it. So we're going to give you the full code for optimistic concurrency control with strict two-phase locking and deadlock avoidance, which is already a nice way of doing transactions. Of course, there are other ways too, but this is the way we're going to show you. And there's actually an implementation of this in the book. So I'm not going to go through this implementation in detail because it's kind of complicated, but we will show the algorithm. We're going to show the algorithm as a state diagram, and you will see exactly how it works. How do we do all of these things together? It's actually the most complicated algorithm in the book. It's 2 pages of complicated code, but the ideas are very straightforward. Okay? So let me give you a simple explanation of how transaction systems work. So the way it works, a transaction system looks something like this. Whenever I start a transaction, like T1, I have here a thread actually running a transaction, and it does things. Reads and writes and reads and writes, but inside the lock. And it talks to a special piece of the system called the transaction manager. So whenever each transaction, when it needs a lock, it will ask the transaction manager. Okay? When it needs a lock, it asks, please give me the lock for cell 55. Transaction manager says, okay, here the lock is for you. But the transaction manager can do many things. It can give the lock, it can delay, it can ask that transaction, it can let that transaction wait because the lock is maybe somewhere else, or it can refuse to give it. It can say, no, you don't get it. Please abort. You must abort. So the transaction manager decides how to give the locks. And when the transaction then, TI, when it has the lock, eventually it does not need anymore. It gives it back to the transaction manager. So see, the transaction manager is managing all the locks for all the cells in the database in a smart way so that all of the transactions are running as much in parallel as possible, but still it's serializable. It's as if all the transactions are running in some sequential order. Semantically, the state changes in the databases are like that. Okay? So the transaction manager is the magician handling the interface between the illusion of sequential, this is serializability, and the reality of the actual parallel implementation. So the transaction manager is actually the core of the system, and this is the part we're going to talk about, and we're going to show you how the transaction manager does this magic stuff. Okay? So let me go back now to the chat. So this is all I'm going to say today. You can see transaction is a very interesting area, super important for computing in industry, and quite complex. So I'm going to try to explain it all to you in a nice way so that you understand how the transaction manager works. Okay, let me go back to a question. So the question from Lorenzo is about transactions. So transactions are doing changes, but they might be interfering on a single cell. Like one transaction might be putting money into the account, the other one is removing money, and they're using the same account. And the question is, what about keeping track of changes? We could have a single thread doing actual writes, another thread add changes to a queue. So if I understand right, the idea is that if I add money to an account and another transaction removes money, somehow I can combine those two. If one transaction adds 100, the other one removes 20, then it's like I'm adding 80. And the answer is yes, that is actually a useful optimization for money. So the money obeys some kind of algebra. It is commutative, it is associative, and because of that algebra, we can actually combine transactions and go even faster. So we can even make two interfering transactions, we can actually make them run really in parallel by merging them in a sense. Okay, so that is possible, and some very high performance systems, they do that. Okay, so the question, it's a very good question, is definitely possible, but I will not talk about it in this course, but in some very high performance systems for certain application, like banks, where money, for example, obeys certain laws, certain algebra. This kind of optimization is done. Okay, and of course it makes the implementation more complicated, but it can give a boost in performance, in the parallel performance. So the question is, it is definitely possible, but I'm not going to talk about it because I want first to show you how the regular transaction manager works. And you can always optimize. Huh? So this is an optimization that can be done. Okay, for the question by Lorenzo, kind of answers it. So if you can look around on Wikipedia, Google is your friend and can actually give you some of these protocols. But the first thing is to understand the regular transaction manager. Okay, so let me stop here. I'm not sure if people have other questions. So we talked about tuple space. So it's actually a very nice thing. Publish, subscribe. I talked about monitors, and you can see that it's an interesting way of managing threads that collaborate using a weight set. And finally, I'm starting now talking about transactions, which is about how to update huge quantities of information in a very robust and high performance way. So that's a very important use case for shared state. Okay, so that's all for today. Thank you very much for coming here so early in the morning. So I know it's very difficult to wake up so early, so I'm very happy for everyone who's here. I will stick around a little while to answer any more questions that people have, but now the course is done and you are free.